In my last video on Apollonius' Treatise on conic sections, we looked at how, given certain information regarding a conic section, how we can reconstruct the conic so that it's in agreement with that information that we've been given. And that really brought us to the end of Apollonius' first book. So in this video, I'm going to start off, make a start on Apollonius' second book. In Heath's translation, this is the first proposition that I'm going to go through is proposition 28. Now we're going to be looking at specifically the hyperbola, and we're going to be going through some properties of asymptotes of hyperbole. So let me just explain the diagram that's on the board behind me. So here's our hyperbola, and PP primed is a transverse diameter, obviously extended as far as we need to, and this red line here through the point P is the tangent line to the hyperbola at the point P, and I'll explain the rest of the diagram as we go along. So on that tangent line, what we're going to do is we're going to cut off two finite segments, PL and PL primed. They're going to be equal in length, and such that PL squared is equal to PL primed squared is equal to a quarter P times P primed. So PP primed is the length of the transverse diameter. I'm using this lowercase p here to represent the parameter of the hyperbola with respect to that diameter PP primed. So to avoid any confusion here, because I've used PL in previous videos, I've used that to represent the parameter, and not using PL here to represent the parameter is the lowercase p. Sometimes this quantity p times PP primed is sometimes referred to as the figure of the conic. I don't know where the term comes from, but it does seem to be an important quantity that comes up from time to time, that the length of the transverse diameter multiplied by the parameter of that transverse diameter is called the figure of the section. So in other words, I'm going to pick on particularly the PL here. Whatever I do here applies equally well to PL primed. So in particular, we've got PL is equal to a quarter P times P primed. We also know that the ratio of P to PP primed is equal to P times PP primed ratio P primed squared. So this is really a consequence of Euclid, probably books 6 proposition 1, that allows us to say this, and therefore this bit here, just looking at, oh sorry, that should be PL squared, that's equal to 4 PL squared, and this thing here, well, PP primed, the midpoint of PP primed is C, so CP is equal to CP primed, so therefore PP primed is equal to 2 CP, so this is equal to 2 CP squared, which is equal to 4 CP squared. So this ratio here, P primed, is equal to the ratio of 4PL squared to 4CP squared, which just reduces to PL squared to CP squared. Okay, so now what we're going to do is through that point L on this tangent line, we're going to draw CL, so a line from the centre of the hyperbola through L, and we're going to produce it, and we're going to assume that it actually touches or intersects the hyperbola at the point Q, and this is where we're going to get our contradiction from further down the line. So it's the assumption that this line intersects the hyperbola, which is going to lead to that contradiction. But let's assume that it does intersect. in which case we can draw a line ordinate-wise from Q to the diameter PP primed, and so that will be QV, and naturally that's going to be parallel to PL. In fact, it's going to be parallel to PL primed as well, because all the chords that PP primed bisect will be parallel to the tangent line to the hyperbola at the point P. So what we get is that triangle CPL is similar to triangle CVQ. So I'm just using this symbol to indicate that the triangles are similar, and therefore I can say that the ratio of PL to CP is equal to the ratio of VQ, or QV should I say, actually, that would be better for me to say QV. QV to CV. And therefore PL squared to CP squared is equal to QV squared to CV squared. So therefore, notice that we've got the same thing here as we've got here. We can conclude then that P to P primed is equal to QV squared to CV squared. Okay, but right, probably in I think the second video that I made, we showed that the ratio of QV squared to PV times P primed V is equal to the ratio of P to P primed. So in that video, I think it was the second video, I would have used PL, I think, instead of the lowercase p. But remember, we're using lowercase l to represent the parameter here. So again, we've got P ratio PP primed in both of these. We've also got QV squared here. So that means then that this PV times P primed V must be equal to this CV squared. Okay, and now let's just have a look at the diagram. So if we look at this PV, so what is PV made up of? Well, we can think about it as CV minus CP, for example. And P primed V, we could think of as P primed C, or even CV plus CP primed. But remember that CP primed is just equal to CP, so we can think of P primed V as being the same length as CV plus CP, and therefore PV times P primed V is simply going to be equal to CV minus CP times CV plus CP, which is of course a difference of two squares, as we'd call it in kind of modern terminology, which gives CV squared minus CP squared. So in other words, we've got that this thing here, CV squared minus CP squared, is equal to CV squared, but this is impossible, because unless CP was equal to 0, then this wouldn't be, this is not valid. We know that CP is not equal to 0. It's got a finite, a definite positive length, so therefore we're subtracting something positive here from CV squared. So if we subtract, we've got CV squared, we subtract something positive from it, we can't end up with, again, CV squared. So this is our contradiction. So the conclusion is that, in fact, the line CL does not meet the hyperbola. hyperbola. And we could go through exactly the same argument for PL primed. So we could have drawn CL primed, made all the same assumptions and come to basically the same contradiction. So this line CL, so L is actually going to be further kind of down here. Then the line CL produced is not going to meet the hyperbola at any point, and similarly CL primed is not going to meet the hyperbola at any point. So these lines CL and CL primed are what we call asymptotes to the hyperbola. Now, from modern kind of terminology, asymptote is something that's quite commonly we quite commonly come across it, particularly in relation to hyperbole, and it's understood that a hyperbola will get arbitrarily close along the as you move along the branch. It will get arbitrarily close to the asymptote. We don't know that at this stage. All we've proved is that such a line does not intersect the hyperbola. It doesn't meet the hyperbola. So further down the line in Apollonius's work, and I think I've got it down as one of the propositions that I want to cover, that any that we don't know that this is kind of the this CL is a line that the hyperbola gets arbitrarily close to. We've got to prove that. That's something that's got to be proved, so we can't take that for granted at this stage. For all we know, CL and CL prime could actually be quite far away and remain quite far away from the hyperbola itself. So that's the first part of proposition 28. I'm going to move on now to the second part. So moving on now to the second part of proposition 28, what we're wanting to prove now is that for a double branched hyperbola, both branches have the same asymptotes. So in the diagram here we've got our hyperbola, and this red line, PP primed is a transverse diameter, extended if we need to. The red line here is the parallel, the tangent line to the hyperbola at the point P, and the red line here is the tangent line to the hyperbola at the point P primed. So L and L primed are chosen in exactly the same way as we did in the first part, namely that PL squared is equal to PL primed, squared is a quarter P times P primed. And on the tangent over here as well, we choose M and M primed in exactly the same way. So PM squared is equal to PM primed squared is also equal to a quarter P times P primed. So from this it obtains that PL is equal to PL primed is equal to PM is equal to PM primed. Okay, so from the diagram, the way that I've drawn it, it would seem that this line here through L, C and M primed is a straight line. Actually, we're not free to assume that at this stage. That's actually what we're wanting to prove. And similarly, the line through M, C and L primed, we can't assume is a straight line either. That's what we're wanting to prove as well. So then the asymptotes would be the same. For all we know, MCL might be more like that, so it's got a bit of a kink in it. We hope that that's not the case. We're wanting to rule out that possibility, but we're not quite at that stage yet to say that. Okay, so the tangent to the hyperbola at the point P and the tangent to the hyperbola at the point P primed are parallel lines. Now, actually, this is something that Apollonius just kind of assumes. It seems obvious that should be the case. Apollonius does assume it in his work. In Heath's translation, there is a little note that says that even though Apollonius didn't prove it, there's another Greek geometer that supplied a proof of the parallelism of these two lines. It's not a difficult thing to to prove. It's only a few lines long, but we're going to take it as given just for the time being that LL primed is parallel to M primed. So we're going to take that as given. Okay, and we've also got that obviously PC P primed is a straight line. So therefore, let's get a different coloured pen. The angle here, so angle M primed P primed C is going to be equal to the angle LPC. And we know that CP is equal to CP primed, and we know that M primed P, sorry, these should be primes up here actually. M primed P primed is equal to LP. So we've got that here and here. So that would suggest then that triangle M primed P primed C is congruent to triangle PCL. So if they're congruent, then not only is angle CP primed M primed equal to CPL, we've also got the angle P primed M primed C is equal to angle PLC, and also the angle M primed C P primed is equal to the angle PCL. So what that proves then is that the line LCM primed is a straight line, and we knew that CL was an asymptote to the first hyperbola, CM primed was an asymptote to the second branch over here, and it turns out that LC M primed all lie on a single straight line. So therefore the two branches of the hyperbola have the same asymptote, at least when it comes to this one here. But in exactly the same way, we can show that L primed CM is a straight line, and that would be exactly the steps of the proof of that would be exactly the same. So we'd show that triangle CP primed M is congruent to the triangle CP L primed. So both of these asymptotes suffice for both branches of the hyperbola. So moving on now to the third part of this proposition 28. What we're wanting to prove in this part is that hyperbola and its conjugate will have the same asymptotes. But just before I get on to the proof, explaining the diagram and the proof, I just need to prove just a little aside thing. So the relationship between the transverse diameter and the secondary diameter of a hyperbola is as follows: that P primed ratio D primed is equal to D primed to P. So P is the parameter of the hyperbola with respect to the transverse diameter PP primed. So from this we get, of course, that D primed squared is equal to P times P primed, and therefore P primed squared ratio D primed squared is equal to p primed squared ratio p primed. Okay, now p primed is equal to 2cp, where c is the midpoint of pp primed, and similarly dd primed is equal to 2cd. So what we get from here then is that 4cp squared to 4cd squared is equal to 4cp squared to p times p primed. We can almost think of this as dividing through by 4, and we get cp squared to cd squared is equal to cp squared to a quarter p times p primed. So the result of this is that a quarter p primed is equal to cd squared. So CD is half the length of the secondary diameter, and this is, as I've said, P times PP prime. That's the figure. It's called the figure of the conic, using this transverse diameter and its parameter. Okay, so now coming back to this diagram, what have we got? We've got a parabola here and here, with transverse diameter PP primed, and then DD primed is going to be a secondary diameter to that transverse diameter. And we're going to, using proposition 26, which I proved in the last video, we're going to describe another parabola, this blue one here, which is the conjugate, hyperbola, with the conjugate hyperbola to this original hyperbola here. So the transverse diameter of this conjugate is going to be dd primed, and the secondary diameter to that conjugate is going to be p primed. And then what we're going to do is we're going to draw the tangent lines in at p and p primed on the original hyperbola, and the tangent lines at the point d and d primed on the conjugate hyperbola. So this tangent line and this tangent line are parallel. Similarly for these two tangent lines here, so therefore the red shape here is going to be a parallelogram. And with regards to this DD primed, the chords which DD primed bisects are the chords that are parallel to the tangent line at either D or D primed, but they're also parallel to the transverse diameter. So this is something that I went through, I think, in the second video. So therefore, this line M primed, L primed, and ML, which are the tangents at D and D primed, are going to be parallel to PP primed here. Moreover, PP primed bisects DD primed at the point C. So not only does PP primed bisect the line DD primed, it actually bisects the parallelogram, this red parallelogram here. So what we can say from that then is that PL is equal to PL primed, which is equal to P primed M, which is equal to P primed M primed, which is also equal to PP primed bisects DD primed is equal to CD. So now squaring all of these, I'll get that PL squared is equal to PL primed squared, etc. is equal to CD squared is equal to a quarter P times P primed. Therefore, CL, LCM primed and MCL primed are asymptotes to the original hyperbola. Okay, so MCL primed and M primed CL are asymptotes. Asymptotes to this parabola, this hyperbola here. And we can do a similar thing for the other hyperbola. With respect to the other hyperbola, we can show that, what can we show? D L primed is equal to D M primed is equal to D primed M is equal to D primed L. This is equal to CP, which is going to be a quarter. So it's the parameter with respect to the other diameter. So I'll just call that maybe Q times D primed. But this would be exactly, sorry, that's not quite right. Because I need to square all of these. So it's DL primed squared, etc. equals CP squared. And it's this, sorry, that equals a quarter Q times D primed, where Q is the parameter. I'm going to use Q to represent the parameter of the blue hyperbola here with respect to D prime. And therefore, all of these quantities satisfy the right conditions for, where are we? M primed CL and L primed CM to also be asymptotes of the blue hyperbola in here. So this is going back to the first part of the proposition that I proved. So therefore, M C L primed, M primed CL asymptotes of the conjugates hyperbola. So as we can see then, a hyperbola and its conjugate share the same asymptotes, and that's the end of the proposition. Let's have a look now at proposition 29 from Heath's translation of Apollonius's work. So, okay, I'm going to explain the diagram that goes with this proposition, and at some point the proposition itself will get introduced. Now there is quite a bit of explanation to go through here, partly because I've got to clarify exactly what this diagram is representing, because the appearance of the diagram is slightly different to what it is that it's actually representing, which will become clear as we go on. It seems a little bit misleading in a way, but I'll explain that as we go along. So what we've got here is a hyperbola, and the lines CL and CL primed are asymptotes. So asymptotes formed in exactly the same way that we would have done in proposition 28, namely choosing L and L primed on that tangent line at this point P, such that PL squared is equal to PL prime squared is equal to a quarter of the figure of the hyperbola. Okay, so LL primed is tangent to the hyperbola at the point P. CP is a diameter, and this blue line here, I don't know if you can see that it's blue actually, but in between the hyperbola and the asymptote CL, this is another line, and what we're going to assume is that this is actually another asymptote. So what we didn't prove in proposition 28 is that the asymptotes that we found, that we just showed that the lines CL and CL primed produced never meet the hyperbola. But what we never actually showed is that the kind of angle between those two asymptotes is minimal, in the sense that if we choose another line in between those two asymptotes, this new line can't itself be an asymptote. Well, we're going to assume that here. We're going to assume that we have got another line here between the asymptotes that is itself an asymptote. In other words, it doesn't meet the hyperbola. So what we're going to aim for is a contradiction. What we're wanting to show is that between those two asymptotes that are determined by proposition 28, there can be no other asymptotes in between those two asymptotes. This is the proposition that we're wanting to prove. Okay, and this is where it starts to get a little bit confusing with the diagram. So I'm going to try and clear this up as best as I can. So this line here through P, so it's a green line, this is supposed to be a line that is parallel to the asymptote CL. Okay, so we've got the green line and we've got CL. They're supposed to be parallel. And then we've got this other line here, this blue line, which is not parallel to either of those. It's definitely not parallel to CL because it meets CL in the point C. And therefore it can't be parallel to this other line up here. So therefore it must meet this other line at the point K. So that's this K that we've got just here, for example. So this was the original asymptote CL, and this is the new line that we've drawn here. Now, obviously in the diagram, it doesn't look parallel. The reason for that is because what's going on in between L and R here, or between maybe P and K, or whatever, which way you look at it, it's potentially going on over a huge distance. So the actual situation has kind of been condensed down into this tiny diagram. So even though PK doesn't look parallel to CL in this particular diagram, it's supposed to be. This could be stretched out over a much greater distance. So for all intents and purposes, PK is, in this situation, parallel to this asymptote CL, even though it doesn't look like it from the diagram. And then wherever PK meets this new line, this blue line in the point K, we're going to draw a line through that point parallel to LL primed. So that's going to meet the asymptotes in R primed respectively, and the hyperbola in QQ primed respectively, and is going to be bisected, or at least should I say QQ primed is going to be bisected by the diameter through P. So that's the situation that we've got to start with, and I'm going to move now on to the proof of this proposition. Okay, so the start point with this, with the proof of this proposition is as follows. So we can recognise that triangle CP L primed is similar to triangle CV R primed. So from this we get that CP to CV is equal to PL primed to VR primed. Similarly, triangle CPL is similar to triangle CVR, and therefore, again, CP to CV is equal to PL to VR. So CP to CV, CP to CV, therefore this must be equal to this. So PL primed to VR primed is equal to PL to VR. But PL primed is equal to PL, and therefore we can conclude that VR is equal to VR primed. Okay, so that's something that we're going to need to use further down the line. Okay, and now we've also got, so this is where again you're going to have to use your imagination a little bit and imagine PKRL as a parallelogram. So PKRL So that would suggest that obviously pk is equal to lr, but more importantly pl is equal to kr. And because of the construction of this situation, namely that the blue line is kind of outside of the hyperbola but inside of this asymptote here, CL, then the distance KR has to be less than QR. So therefore QR is greater than PL. But we can also say the following, that PL primed is equal to PL is less than QR, but QR is less than VR, has to be, but VR is equal to VR primed. Because we've already shown that here. So VR is equal to VR primed, but VR primed itself is less than QR primed. So therefore we can conclude that PL primed is less than QR primed. So now putting these two together, we get that if I just move up here, QR times QR primed is going to be greater than PL times PL primed. It's looking a bit wonky, isn't it? Times QR primed is greater than PL times PL primed. I don't know if that's any better. But PL times PL primed is just equal to PL squared. Okay, and now let's have a look at the similarity, this particular similarity again, which is triangle CPL is similar to triangle CVR. Then I get the following, that RV squared, sorry, RV to the ratio of RV to CV is equal to, so RV, CV, the ratio of PL to CP. So squaring everything, now I get RV squared to CV squared is PL squared to CP squared. But we know that PL squared is equal to a quarter the parameter P times P primed, and also that CP squared is equal to a half P primed squared, which is a quarter P primed squared. So therefore PL squared to CP squared is equal to P dot PP primed ratio P primed squared, and then you can kind of cancel the PP primed off each side, and you're just left with P ratio P primed. So P lowercase p is the parameter of the hyperbola. But PP primed is equal to QV squared to PV times P primed V. So this was back in the second video I think that I made. This was effectively the one of the fundamental relationships of the hyperbola that emerged from the definition itself of the parameter. So it might be worth, if you need a reminder on that, going back to somewhere in video 2. Okay, but as I showed in proposition 28, from this we'll get QV squared. PV times P primed V is going to amount to CV squared minus CP squared. Okay, so now we need to have a look at similarity again. Is it? No, it's not. No. We've got RV squared to CV squared is equal to, so we know that RV squared to CV squared is the same as PL squared to CP squared. But that was the same as P to PP primed, which in turn was equal to this thing. So therefore, RV squared to CV squared is equal to QV squared to CV squared minus CP squared. And just rearranging this, we get RV squared to QV squared is equal to CV squared to CV squared minus CP squared, and then it's kind of a separando kind of argument. So we get RV squared minus QV squared to QV squared is equal to, it's going to be CP squared to CV squared minus CP squared. Rearrange to get RV squared minus QV squared to CP squared is equal to QV squared ratio CV squared minus CP squared. But we've already seen that this is equal to RV squared CV squared. RV squared CV squared is equal to PL squared CP squared. So therefore, RV squared minus QV squared ratio CP squared is equal to PL squared to CP squared. So notice now that we've got CP squared, CP squared. So that means that this must be equal to this. So therefore, RV squared minus QV squared is equal to PL squared. So we're nearly there now with this. Let's have a look at this thing now. This is the last leg really. So RV squared minus QV squared is equal to RV plus QV times RV minus QV. So RV, now I've got to make sure I'm getting this the right way around. So RV is equal to VR primed. So we've already shown that here. VR is equal to VR primed plus QV, and RV minus QV is just going to be QR. But VR primed plus QV is just QR primed. So what do we conclude from this? Therefore, PL squared is equal to QR primed times QR. And this is our contradiction, because we've already shown that QR times QR primed has to be greater than PL squared up here. So that is our contradiction right there. And that proves the proposition. So just to recap what the aim was in this proposition, the aim was to show that between the asymptotes as they were determined in proposition 28, that in between those asymptotes we can't choose another line through the point C, through the centre of the hyperbola, such that it itself is also an asymptote. So in a sense, those two asymptotes determined by proposition 28 are kind of minimal. The angle between them is minimal. We can't choose another line, another asymptote between them. And that's the end of the proposition. So I'm going to move on now to proposition 34. We're going to move on now to proposition 34 in Heath's translation of Apollonius. And let me just explain the diagram that goes with that proposition. So we've got a hyperbola here and two asymptotes to the hyperbola. And then from any 2 points on one of the asymptotes, so uppercase H and lowercase h here, we're going to draw two parallel lines, making any angle whatsoever with the asymptote, such that they intersect the hyperbola at the points uppercase Q and lowercase q. So it doesn't matter what angle they make with the asymptote, as long as the two lines are parallel and they intersect the hyperbola. And then from these points uppercase Q and lowercase q, we're going to draw two more parallel lines. That's these green lines here, if you can see that they're green. From the hyperbola to the second asymptote. Again, the angle that these lines make with the asymptote is completely irrelevant. I could draw them as I've drawn them here, or I could draw them further over here. As long as they actually meet the asymptote, it doesn't really make any difference. And then from between the points uppercase Q and lowercase q, we're going to draw the chord of the hyperbola joining those 2 points, and then produce that chord to the points uppercase R and lowercase r, which are where that chord will intersect the asymptotes of the hyperbola. And what we're wanting to prove here is the following relationship, that the rectangle contained by uppercase HQ and uppercase QK is equal to the rectangle contained by lowercase HQ and lowercase QK. So the reason that I've included this particular proposition in this video is because prior to reading Apollonius, I didn't actually know that hyperbole had this property, so it was quite an interesting property. What makes it particularly nice is the symmetry that it possesses. Mathematicians, geometers like symmetry and patterns, and the proof of it is actually surprisingly straightforward. So I decided to include it in this video. Despite its simplicity, don't be under any illusions that it's not a useful proposition. One thing when you read Apollonius is that you soon realise that all of the propositions that are included are either included because they're used in the proofs of propositions further down the line, or they are in and of themselves a substantial, significant result. So for example, in the last video I showed how to construct certain conic sections from given data, that those results in and of themselves are substantial. It doesn't really make any difference whether they can be used for in the proofs of additional propositions. It turns out that they can, but even if it was just those results, they are substantial enough results to stand on their own, really. This is not such a substantial result, but it is something that is necessary further down the line. Its use might not be immediately apparent, so it might not be used in the next proposition or even the one after that. It might be quite some time, but it will eventually be used. Okay, and in the proof of this, we're going to have to assume that proposition 32 in Heath's translation has already been proved. So proposition 32 says that simply for a hyperbola and a chord such as this blue one here that goes through Q and meets the asymptotes R and R, then for any such chord we'd have that RQ is equal to RQ. So uppercase RQ is equal to lowercase rq. From this it follows quite easily that QR, so this distance here, is equal to QR. So this is fairly easy to see. So if I draw two copies, for example, of QQ, and if I add to one of them RQ, then add to the other one QR, because this is equal to this, and obviously this is equal to this, then the whole thing here is going to be equal to the whole thing here, and hence we get this equality as well between these two magnitudes. So from this point, taking these two results, what we get is that RQ times QR is equal to RQ, the rectangle contained by lowercase rq, and lowercase q and uppercase r. And then rearranging this, so to speak, we get RQ, the ratio of uppercase RQ to Q lowercase q uppercase r is equal to RQ ratio QR. Okay, and now just we're going to leave that there, and we're just going to go on to a slightly different path now, and notice that triangle RHQ is similar to triangle RHQ. So from this it follows that RQ ratio QR is equal to HQ ratio HQ. And from these two results now, it follows then that RQ ratio QR is equal to HQ ratio HQ. So we're going to need that in a second. And now we can also recognize that triangle, let me get this right, QRK is similar to triangle lowercase qrk. So therefore, the ratio RQ to QR is equal to the ratio QK to uppercase QK. And again, using now these two results, it follows that, because these two are the same, we get that HQ ratio HQ is equal to QK ratio QK. And then the next step is obvious. HQ, it's just a simple rearrangement. The rectangle contained by uppercase HQ and uppercase QK is equal to the rectangle contained by lowercase HQ and QK, which is exactly the result that we wanted. And that finishes the proof of proposition 34. Okay, so I'm going to wrap up this video there. I'm not going to go through any more propositions in detail from this particular section for this video. That's not to say that there aren't other interesting propositions regarding asymptotes that Apollonius proves. In fact, just looking through the book now, so we've done proposition 28, proposition 29. This is the numbering that Heath uses in his translation. Proposition 30 is effectively a converse proposition to proposition 28. Proposition 31 is interesting because it shows that given the asymptotes of a hyperbola and a point on the hyperbola, that you can actually reconstruct the hyperbola itself. So this is again showing that these things exist, that given certain data you can make these constructions. Proposition 32 I've already kind of mentioned. Propositions 35 and 36 are interesting. I'm not going to go through them in detail, but they are interesting, they're just worth mentioning. So proposition 35 is quite similar to proposition 29 in many respects. So if these are the asymptotes of a hyperbola, and we've got our hyperbola in here somewhere, then proposition 29 said that if I chose another line through the intersection points of these two asymptotes, namely at the centre of the hyperbola, then it would intersect the hyperbola at some point. Proposition 35, it's slightly different though, because what it says is if I choose a point on this asymptote here, so we're just looking at one branch of the hyperbola here, choose a point on the asymptote that is not C, and draw a line parallel to the second asymptote, then this line must intersect the hyperbola at a unique point. So it's just got one point of intersection, so here, for example. And then proposition 35 is used in the proof of proposition 36, which shows really a key characteristic property of asymptotes in relation to hyperbole, namely that as you move further and further along the branch of the hyperbola, you get arbitrarily close to the asymptote. So the distance between the asymptote and the hyperbola will fall below any given magnitude, any given positive magnitude, no matter how small. So it's really a fundamental property, really. I'm not going to go through it in this video, but it's there in Apollonius's work. There are a couple of other propositions as well, propositions that are in and of themselves not particularly special or interesting, but will probably be used further down the line. So I'm going to finish the video there. We're maybe a third of the way through Apollonius' second book, so hopefully by the end of the next video I'll get through maybe the end, through to the end of book 2. So I just want to thank you once again for watching this video, and I look forward to seeing you in the next video.